main memory today, like I forgot to put this on. We'll do a lot on main memory today. It's a big subject, and I cannot cover all of it, obviously. And this is going to be mainly DRAM-based main memory. These days, because DRAM is having issues, some of which we'll talk about, scaling issues in terms of getting very large capacity main memories, a good chunk of research in computer architecture is dedicated to looking into emerging technologies like phase change memory that I briefly mentioned last time. Can we build main memories using something other than DRAM? Can we use flash, for example, flash memory as part of your main memory that's accessible by loads and stores? Well, the downside is flash has very long access latencies. So if you put it as part of your main memory, now your load store takes like microseconds. You perhaps don't want that, right? Well, you go through the cache hierarchy, and the miss from DRAM for load store can take tens of microseconds, and you may not want that. Okay, but this will be all within the context of DRAM. Maybe when we'll have time in one of those later lectures, I can introduce you to some of those other technologies, which is, I think, interesting. But the fundamentals are really the same in the end, right? In all levels, you exploit locality to improve performance, and you will see it's no different in DRAM. And I showed you the picture of a bank. That's an abstraction. You can go down a bank, and you will see a similar structure. You'll see sub-banks, if you will, that look similar. And when you go up, as we will see today, you'll see something similar again. So it's even within the design of a chip, you have some hierarchical structure that exploits fundamental characteristics. As you make the size of this thing, bank, smaller, it becomes faster. Okay. And as you buffer stuff, within each hierarchy, you exploit locality. So those fundamental principles will never change, regardless of the technology. Technology just changes, if you will, what is the latency to access a cell? What is the latency to sense it? What is the latency to read it out or write to it? And these are very much dependent on technology. For DRAM, for example, writing into a DRAM cell and reading from a DRAM cell has similar latency, at least today. But for some other technologies, I mentioned this briefly last time, like phase change memory, to write into a cell, you need to melt the material that stores the cell, that stores the data in one format versus the other. When the material is melted, it's a 0. When the material is not melted, it's a 1. So that melting takes a long time, because you need to heat the cell up to, I don't remember the exact number, but a high temperature. So DRAM doesn't work that way, right? You store charge into a capacitor. So in that particular case, phase change memory, it takes much longer, like 10x longer, to write into the cell than to read from the cell. So you can imagine how that can change your design decisions, right? You might want to bias your hierarchy such that you don't do much writes. You don't expose many writes into your main memory. Okay? All right. But before we start, your homework 5 is due today. How are people finding it? Easy? Fun? You like the reverse engineering questions in caches? No? Well, hopefully you'll understand very well once you solve the reverse engineering questions. We might have similar questions on the exam. And you can look at our previous exams. There are reverse engineering questions in the previous exams also. Okay. And how are people finding the TLB question? I hope it's not that hard. You've already seen it, right? Basically what a TLB is, it's a cache, right? It's a cache for the page table. We will cover this briefly, but you should know this from 213 or 243. It really caches page table entries that you accessed recently. Okay. Homework 4 grades. Looks like we have a distribution here. Previous homeworks used to be around here, so I'm a little bit worried. Either the homeworks are getting hard, or you guys have a lot to do in the semester. But hopefully next homework everyone will get 105, well, the top score. Lab assignment, you have a lab assignment to April 6th, and don't forget the extra credit. If you actually explore the cache and provide high performance by different caching policies, you can actually get significant extra credit. And we will see some people got extra credit for lab assignment 4. That's why those people are here versus somewhere else. This is the lab 4 grades. I think this is the perfect score, right? Maximum possible points is 700. And we've got 19 people who got the maximum possible score. Out of them, 3 of them actually optimized their designs and got the fastest execution time. That's where the 10% extra credit comes from. So hopefully you'll figure out what was wrong in your design, or if we graded incorrectly for some reason, you should really come to us. Okay, so these are the correct designs. The 19 people who got the correct designs, and top 3. There was a good cutoff between the top 3 and the rest, if you will, 5% cutoff in terms of the relative execution time. So Eric, Art, and Alex will get their extra credit as well as prizes. But I don't have the prizes today, so this will happen later. So I think one interesting thing is here, the critical path James had was the lowest, but the cycles was one of the highest, if you will, at least among the top 10. So you did a very fast design, but it executed the instruction. It took a little bit longer to execute the instructions. So if you optimize for CPI a little bit more, maybe you'll be up there. So you figured out that you did well on that 4, huh?
I did not try to optimize it.
You did not try to optimize it? Maybe my design. Okay, that could happen too, right? Maybe you designed it in a way that it happened to be optimized. That could also happen. Okay. Reminder. Hopefully this is not a surprise, but there's a midterm coming up on April 11th. And everything covered in the course can be on the midterm. Of course, we'll have more stuff on the midterm and the topics that we covered after the first midterm. But everything can be on the midterm. And you can bring in 2 cheat sheets. Okay, you have a question?
Is it going to be just as long?
It's going to be just as long. I don't know because I haven't prepared the midterm yet. Or we haven't prepared the midterm yet. But it could be. So, do people want a review session? Yes. Okay, I guess it'll be useful. I don't need to add. So we'll have a review session. I'm not sure about using the lecture time as a review session, so we might do it in one of the evenings. Could be Monday evening or Tuesday evening. What do people feel like weekend evenings? No. Okay, so Monday or Tuesday evenings would be much better. In class, yeah, I understand in class would be best, but we have materials to cover also. So we'll see. We'll make the trade-off. Okay, last lecture, we wrapped up basic caches. These are a bunch of stuff we talked about. I would like to remind you, we talked about multiple outstanding misses and multiple accesses per cycle. Those were the last things. And you should know how these work. Because actually, I think you're going to implement multiple outstanding misses in the next lab, right?
Lab 6, they will.
Lab 6, yes, which is going to come on soon. We started main memory. We talked about interleaving, bank, rank, and some of the basics. Today we'll continue with main memory, DRAM organization and issues. Yes.
For the rest of the labs, the all simulation, are we going back to Verilog?
We're not going back to Verilog. So, what do people feel about that, by the way? People don't want to go back to Verilog. So, it's easier to debug. That's right. Yeah. So you see the advantages of high-level simulation. The purpose is different, but it's easier to do some things in high-level simulation. But computer architecture spans a very wide thing, so I want to give you the full experience. As you're a computer architect, you can go and design the logic circuits and do design at Verilog, or do design at this high level, or do both when you work for a company or when you do research. So you should be comfortable with both. And cognizant of when you should employ what kind of simulation methodology. And hopefully the last 3 labs will give you a good idea of the advantages and disadvantages of high-level simulation. Okay, I'd just like to remind you the concept of interleaving. We covered this in many different ways so far, and we'll see how this is employed in DRAM, in a real DRAM system. Well, the problem is if you have a single monolithic memory array, it takes a long time to access and doesn't enable multiple access in parallel. So we would like to reduce the latency of memory array access and enable multiple access in parallel. And the idea is simple. You divide the array into multiple banks that can be accessed independently. And one issue that comes with interleaving is bank conflicts, if you will. Bank conflicts happen because the data that you are trying to access concurrently, either in consecutive cycles or at the same cycle, happen to map to the same bank. Right? So data mapping is important. If you don't map your data nicely into different banks, you can get a lot of bank conflicts. And we've seen some ways of alleviating that, or how that interacts with the stride in vector processors we've seen when we covered vector processing. So you should know about the different design choices here. So let's go into DRAM a little bit to bring some of these concepts together. This is a slide I have shown in the last minutes of the last lecture. DRAM subsystem is organized hierarchically. Basically, you have a channel, one or more channels, which contain one or more DIMMs, which contain one or more ranks, which consist of one or more chips, which internally consists of a number of banks, and you know that a bank is a two-dimensional array of rows and columns. And in each column, you have a number of DRAM cells. The column can consist of multiple bits. And this is the high-level DRAM bank structure I drew. You should be comfortable with this. And we'll cover this in a little bit more. Basically, if you look at it in a little bit low level, these are the DRAM cells. And each cell is connected to multiple bit lines and a word line, if you will. This word line is activated when you activate the row of cells. And this is the row of cells here. And you can have a column of cells that contain multiple of these together. So each cell is also connected to a sense amplifier, which basically amplifies the charge stored here to detect whether a 0 or 1 is stored, and also traps that charge, if you will, in an SRAM-like cell here that is called the row buffer. So the row buffer is essentially a bunch of sense amplifiers that sense the data stored in each cell within the row and store it here to access, because you cannot access the data from the array directly. Whenever the DRAM controller issues a read or write command, data is accessed from the row buffer. Okay. Yes?
From the homework question on the memory, I got the impression that banks were made out of smaller chips. Or banks were made out of smaller chips.
So let's cover this, and it'll become clear when we get to it. Okay, so this is a bank. We'll build up what is a chip, and we'll also build down at the end so that you get a good picture. So a DRAM bank is a two-dimensional array of cells, rows and columns. A row is also called a DRAM page, so if people talk to you about DRAM page, don't be confused. It's basically a row of cells. I don't want to use the terminology of page because page has a specific meaning in virtual memory. You have a virtual memory page, right? It's unfortunate that we overload some of these words. Sense amplifiers, also called the row buffer, and their purpose, again, is to sense the charge in each cell of the row and also store that value in a basically cross-coupled inverter here. Yes?
All right. What are the sense amplifiers made up of?
What are they made of? So they're made up of some circuitry to actually sense the charge.
Right.
I will not go into that. Plus some circuitry to store the sensed value, which is essentially like SRAM. The part that stores the value is like SRAM. The part that senses is not like SRAM. Okay. Well, there could be many designs actually. This is one design. Right? You could actually design this in many ways.
Right. And is this used to also refresh the charge, or is there some other circuit?
We'll get to it. We'll get to DRAM refresh. Good. You guys are interested. So, okay. So each address is a row column pair. And we talked about this, right? You supply the row address first, and then the column address next. And the reason you do that is because you have limited number of pins to the chip. You want to minimize the number of pins. So let's say you don't have a row that's in the row buffer now. I said that you can access the data only from the row buffer. What you need to do, what the controller that controls this bank needs to do is to activate, use a command that's called activate to open the row, which essentially, upon sending this command, the DRAM bank basically takes that row and places it into the row buffer. And then the controller uses the read and write commands to read from and write to columns in the row buffer. And once the controller is done with the row, once it's read the data that's requested by the processor, what it needs to do is to send a pre-charge command to close the row. And that pre-charge command essentially restores a charge into these cells and prepares the bank for next access. So if there's an access to an open row, if the row happens to be in this row buffer, then there's no need to issue this activate command because the row is already there. Right? You can simply keep issuing read and write commands. So this is a picture I had shown you earlier. This is a pictorial animation of DRAM bank operation. Initially, let's say your row buffer is empty, and the processor needs to access the address at row 0, column 0. What the controller needs to do first is to send the row address and send an activate command to the DRAM bank. What the DRAM bank does is essentially activates that row, basically places that row into the row buffer, and then the controller sends a column address, and what the DRAM, as well as a command saying that I want to read from this column. Let's say we're reading. And what the DRAM bank does is essentially muxes out the appropriate column from the row buffer and sends it back through the data bus back to the controller. Now, row 0 is in the row buffer. Let's say the next access is to row 0 again and column 1. In this case, the controller sees that it has some structures that keeps track of which row is open currently in the bank. And the controller sees that the access is to the same row that's in the row buffer, so this is called the row buffer hit. The controller only needs to send the column address, in this case, and a read command to DRAM. And the DRAM bank takes out the specified column and sends it back to the controller. And if there's another access to the same row, but not to a consecutive column, if you will, then that's again a row buffer hit, and the controller needs to send only the column address. And let's say now you have an access to a different row, row 1. The controller realizes that row 0 is in the row buffer. What it needs to do is bring row 1 into the row buffer, which means that the controller first needs to issue a pre-charge command. This is called a row buffer conflict. Basically, you're trying to access a row that's conflicting with what is open in the row buffer. The controller needs to issue a pre-charge command, which restores the data in the row buffer into row 0. And then the controller issues an activate command to row address 1. It also sends the row address that it's trying to access. And then after that, after some number of cycles, the DRAM responds by placing the row into the row buffer, and then the controller needs to send the column address command, and the DRAM responds by taking out the data and sending it back. Yes.
Do you write back row 0 before you read in row 1?
So you can think of it as row 0 being written back. Yes, that's what happens essentially. You write back 0. That's an abstraction. At the circuit level, it works in a different way, but essentially you restore the charge in the cells based on the contents of the row buffer. Yes.
Just forgotten this for a second. What comes out of data? Is that a bit or is it byte or?
Oh, okay. So that's good. We will see that here. The interface is essentially, it could be from 4 bits to 16 bits.
Okay.
So you could think of it as, I'll use 8 bits for now. You can think of it as 8 bits comes out of this.
Okay.
And then we're going to put multiple of these together to get 64 bits at the same time. Okay, yes?
So suppose I'm accessing one particular row for a long period of time. So during that period of time, I have to refresh all the other rows too, right?
That's right, exactly.
So will it happen in the same row buffer, or can I use another circuit to take care of that?
No, it has to happen in the same row buffer, which means that
So I have to
you have to put that row back into the array. We'll get to refresh. So that's a good point, though. Basically, you need to refresh all the cells, right? Remember, these rows lose charge over time. And DRAM controller, one of the jobs of the DRAM controller is to refresh these rows so that you don't lose data. And Ameya's point is essentially, when this happens, you're essentially losing these refreshes interfere with normal operation. Right? And the controller needs to ensure that not only normal operation goes on, not only processor requests are satisfied, but also the data is kept intact in the DRAM. So now we have one complication. We'll see a lot more complications in DRAM soon. Okay, so that's the operation. So obviously, a row conflict access takes much longer, right? Because you need to do more things, if you will. You need to pre-charge the row, which takes time, let's say 15 nanoseconds. You need to activate the new row, which takes time, again 15 nanoseconds. And you need to read the row, again, which read the column from the row buffer, again, let's say takes 15 nanoseconds. So it's 45 nanoseconds for a row buffer conflict. Whereas if you get a row buffer hit, the only thing you need to do is to read the row out of the row buffer, let's say 15 nanoseconds. So there's a 3x latency difference between a row buffer hit and a row buffer conflict. And that's why existing DRAM controllers try to optimize the locality in the row buffer, if you will, such that when you open a row, you take the best advantage of it. If there are requests going to the same row, prioritize those requests. Which makes sense, right? That way you reduce the latency, average latency, as well as you maximize the bandwidth throughput you're getting from DRAM. Okay, the DRAM chip. So this was a bank, right? The DRAM chip consists of multiple banks, 2 to 16. Well, it changes depending on, again, that's a trade-off done by, decided by the DRAM manufacturer for many reasons, right? As you add more banks, remember, you need to have logic to figure out which bank the data needs to go to, right, and route the data. But your parallelism increases. Banks share the command, address, and data buses, and the chip itself is a narrow interface. We just talked about this. So if you look at the block diagram of a DRAM chip, if you will, this is what it looks like. This is from a real DRAM data sheet. Basically, you have 8 banks in this chip. Well, these are the row address decoders, essentially this thing that I showed you here. And these are the memory arrays for each bank. So you can send the row address independently to each bank in consecutive cycles. And these are the sense amplifiers for each bank. And you have the column decoder that selects the data from the sense amplifiers and sends it out of the DRAM chip. And there is a bunch of circuitry to ensure reads and writes happen nicely, if you will, in DRAM. But we will not go into that. But this is the basic microarchitectural structure. And you see that you send the row address or the column address. In this particular chip, row address is 14 bits and column address is 10 bits. It happens to be. Okay? So this is all real. And these are the different banks. And we've seen how each bank works. Now, of course, this chip has an 8-bit interface, right? You can only read 8 bits at a time. But a cache line has how many bits? Let's say 64 bytes, right? In many modern processors. So, to be able to read more stuff and also increase capacity at the same time, we have the concept of ranks, which we talked about last time. You have multiple chips operated together to form a wide interface. Let's say you have from one chip you can read 8 bits, but you want to read 64 bits at a time. What do? You put 8 of these together and operate them as a rank, if you will. All chips comprising a rank are controlled at the same time It's like a rank of soldiers, as I said last time, right? They respond to a single command. They share address and command buses, but provide different pieces of the data. Right? One of them provides the first 8 bits, the next one, the next 8 bits, the next one, the next 8 bits. And using this, we can build a module. A DRAM module consists of one or more ranks. So a DIMM, dual inline memory module, that you might have placed in your motherboard at some point, is essentially one or more ranks put together. Okay, I already told you this. So what does a DIMM look like? Basically, you have DRAM chip, and you put 8 of these together to form a wide interface. In this case, I'm showing one rank here. And they all share the command and data buses. The command and data buses, address bus is not shown here for some reason, but it's all shared among these chip. And remember, the chip has 8 banks inside. Right? Well, a number of banks inside. In this particular chip, it was 8. Okay. So you see the hierarchical organization now. So we made the interface wide with a DIMM, right? So this is another way of looking at it. So I want to show you exactly what a chip is, and you have multiple of these chips put together as a DIMM, and they all provide different portions of a 64-bit interface. And this is the channel, if you will. And memory controller essentially asks for 64-bit wide requests from this rank. Okay? So we made this, by having a rank, we made the interface wide. There are advantages and disadvantages to this. Yes?
Does each DIMM has to have one rank, or is it generally the case that it has one rank?
No, it's at least one rank. You could have multiple ranks to improve the capacity. We'll get back to that. We'll take a look at it. Yes?
Is it useful to divide ranks between several modules, or it doesn't matter?
Why would you want to do that?
I don't know. Is there any advantage to having 8 ranks in one module, for instance, or in one DIMM, or 4 ranks in one DIMM, another 4 ranks in another, having 2 modules?
Oh, yeah. You could have 2 modules. We'll get to this. We'll build up. You could have multiple modules to improve capacity, increase capacity of your. Let's say you want to build a DRAM system that has 1 terabyte memory. Right? You cannot have everything in one chip because your latency. I mean, you could build it, but that would not be cost effective from the DRAM manufacturer's perspective. Okay. So advantages of the wide interface. Basically, you have a wide interface, right? You don't need to read 8 bits at a time, right? So it acts like a high capacity. You also gain capacity, right? So basically, this is how you build a higher capacity system that has a wide interface. And it gives some flexibility to the memory controller, or ease of design to the memory controller, because the memory controller doesn't need to deal with individual chips, individual 8 bits. I mean, you might want to actually if you have a chip that has 8 bits, you're getting 1 byte from each chip, and your cache block is 64 bytes, you might want to put 64 of these and control them at the same time, right? Such that with one command, you get the entire cache block. Now there's a reason why this is not done, and the reason is this pins, right? Pins coming out of the processor are very expensive. You can have 64 times 8, 512 pins, and we discussed this. That's very costly compared to only 64 pins. That's why what's done is you have 64 pins and read data in consecutive cycles. The disadvantage of a wide interface is granularity, right? What if you actually want to read 8 bits? Now you cannot. You have to read all of the 64 bits, which means that you waste some energy. Okay. So you can actually put multiple DIMMs together. This answers your question. Multiple modules together, so that you get more capacity. Right? And this is, think of this as part of your motherboard, right? You have these DIMM slots where you insert the memory, insert the modules. The disadvantage is, of course, when you have multiple DIMMs, now you have interconnect. You have these wires that's running out on your motherboard, and your complexity and energy consumption increases as you put more of these. And of course, you need to control it somehow. I'm not going into this more detail, but there could be many different topologies to connect these DIMMs. So if you look at your motherboard, perhaps you can figure out the topologies if you're able to follow those wires. Okay, DRAM channels. I already told you what a channel is. A channel is essentially the DRAM memory controller's interface to a module, if you will, or a set of modules that are hanging off the same address, commands, and data buses. Basically, a channel is specified. It comprises of address, command, and data buses, and everything that shares those address, command, and data buses are on the same channel. In this case, we have two independent channels, right? You put two of these together, and you put two memory controllers. A memory controller can be on the processor chip or off the processor chip. Now you can have two independent memory channels that you can operate independently. Now, what does this buy you? It buys you more bandwidth, right? Of course, it comes at the cost of additional wires that need to go off your memory controllers. You could operate these channels independently, like here, or in a dependent way. Meaning you could think of this as widening the interface, right? You could have a single controller that controls a 64-bit channel here and another 64-bit channel here at lockstep. So when you ask for data, you get 128 bits. Top 64 bits coming from here, bottom 64 bits coming from here. So you could think of widening your interface even more that way. Usually what's done is independent channels so that you can get different pieces of data and different memory access satisfied. Okay, so let's put this all together, if you will. So you have independent memory controllers. Each memory controller controls a channel, and a channel can host multiple different ranks and multiple different modules. And each rank, if you will, contains, in this case, 4 DRAM chips. And each DRAM chip has this two-dimensional structure, rows and columns. Well, each DRAM chip has multiple banks. Sorry, I forgot that. And each bank has this two-dimensional structure, columns and rows, and a cache line is essentially a number of these columns put together. So it's, I don't know, it's a 5-dimensional structure, right? You have channel, you have ranks, you have chips, you have banks, rows, and columns. And data can be mapped anywhere, right? Now you can imagine a physical address. What bits do you use to determine where the address is mapped to, where the data for the address is mapped to? I'll let you think about it. We'll get back to it. So this is another way of representing it, just for you to hopefully understand more clearly. So let's take a top-down view. Are there any questions so far, by the way? Everything is clear? Now you know how the DRAM operates or looks like? Okay. So let's take the top-down view. We kind of built up from the bottom up, but I think it's also important to see the top-down view. I'll go through this very quickly. Yes?
Aren't the channel and the DIMM on the same level?
Aren't the channel and the DIMM? So you could have multiple DIMMs, right? Hanging off a channel. Essentially, a channel controls a DIMM, yes. A DIMM is connected to a channel, but you could have multiple of these. Okay. So top-down view, basically, this is what you would see in a real system. I guess there are multiple memory channels in a multi-core processor, and these are connected to multiple DIMMs. So this is a DIMM. If you look at a DIMM, so I'm going to break it down hierarchically. If you look at a DIMM, you could actually have multiple ranks. So if you look at the front and the back, you could have different ranks in the DIMM. So this is one with 2 ranks, rank 0 and rank 1. And as I told you, each rank is a collection of chips that act together, that are controlled together. And let's break that down. So this is a rank 0, rank 1. So, well, I guess this is one thing I did not talk about. But essentially, rank 0 and rank 1 also share the buses, right? Well, they don't share the bus, but the bus is multiplexed across rank 0 and rank 1. So you can access the ranks in parallel. You could start, this is the memory channel, address, chip select, and data, and there should be a command here, command, you send the address, data, and command to the different ranks and start access in parallel. But only one access can complete because they share the data bus, right? Data channel. Okay? So once we break down the rank, it consists of multiple chips, and it will supply different portions of the data. And let's take a chip and break it down. It consists of multiple banks, which can be accessed independently, so that you can improve parallelism. This is the interleaving concept. And if you break down one of these banks, what you get is a two-dimensional structure, right? Rows and columns. And this is one example. So this gives you some realistic values that exist in existing systems. So you could have a chip with 16,000 rows and a 2 kilobytes, where each row is 2 kilobytes. Each column is a byte, so you can read only 8 bits. Okay? Make sense? Okay. So how do you transfer a cache block? Just to look at an example. I think this is already clear. But what we want is a 64-byte cache block, right? And it's mapped to a single rank. But a single rank can give you 64 bits at any given time, which means that you need to ask for 8 consecutive 64 bits to get the 64-byte block. And that's what exactly the memory controller does. The memory controller says, give me this first 64 bits of the 64-byte cache blocks, and let's say it happens to be map 0, 0, column 0. So you get the first 8 bytes. And then the memory controller asks for the next 64 bits. You get 8 bytes. And then the memory controller asks for the next 64 bits, and you get 8 bytes. Okay? Now, because these are mapped to the same row buffer, DRAM chips are optimized to give you data quickly from the row buffer. This is called burst mode. So many modern DRAM chips employ this, which means that you don't need to access each 8-bit, each 64 bits in this case, one by one. You can tell, I want to burst off 4 of these 64 bits. And the DRAM chip has logic in it to recognize that instead of providing you only one 64-bit, well, I'm talking about chip, but each chip provides 8 bits. So let's talk about the chip itself rather than the rank. Basically, instead of providing only one of the 8 bits, you can tell the DRAM chip to provide 4 of these in consecutive cycles. And what the DRAM chip does in this burst mode is, you specify the burst length. Memory controller says burst length is 4, which means that whenever the memory controller requests something, the DRAM chip in consecutive cycles puts out 4 8-bit values. Okay? So this is to optimize the control of the DRAM chip so that you don't need to request over and over consecutive locations. Make sense? Okay. This is, okay. So let's take a look at the latency components when you access DRAM. Think about the system perspective. When you access DRAM, the CPU or the core is actually requesting some cache block, right? And it needs to go through the memory cache hierarchy. And once you figure out that it's a cache miss, there's some transfer time that needs to happen for that request to go to the memory controller. And within the memory controller, what happens is that request gets queued up because there may be other requests from the same core or other cores. So there's some queuing delay and some scheduling delay at the controller. What the controller does is, the controller receives the cache block address, right? A physical address. Now the controller needs to translate this to DRAM commands, break it out into column, row. So there's some latency involved in that, and there's some latency involved in the controller communicating with the DRAM. Controller needs to send the commands and addresses, and the DRAM bank latency is a large chunk of the latency, and we've already talked about this. So these DRAM commands are also called CAS, like pre-charge. The pre-charge command we've seen. Activate command is also called, at least in all DRAMs, the row address row. Basically, you're accessing a row, and you're giving the row address, and you're telling, give me this row. That's the row address row. Read or write commands to a column are also called CAS, column address row. Basically, you're providing column address and telling the controller to mux out the column from the row. Also, you need to also provide a read-write bit. If you think of the read-write command as a column address row. Okay. So once the data comes out of the DRAM bank, then there's transfer time back to the CPU. So this all takes a long time, and we will see how to tolerate some of this latency. Yes.
Does the controller encapsulate all the different parts of the cache block and send it as one?
Yes.
Does it?
Well, it depends on your design again, right? The controller could send actually every 64-bit. So if you have a critical word first design, you design the controller such that the processor, when it requests address from the controller, the processor also tells, oh, I want this word in this cache block first because my load is waiting for that one, really. Then the controller can be optimized to first read out that critical word from the DRAM. But it may not be as easy, right? Because remember, we have burst mode, and you want to optimize for latency. And if the critical word happens to be at the end of a burst, then you either start bursting from there, which means that you may want to go back and burst from the beginning of that burst in the cache line. So the design has a lot of choices. Okay, multiple banks. We've seen this. This is just to remind you. Multiple independent channels essentially serve the same purpose of multiple banks, except they're even better because they have separate data buses. Right? Remember, banks share the data bus, which means that they can only put out, only one bank can put out data on the bus. Whereas channels, they do not share the data bus, which increases the bandwidth. So enabling more concurrency requires reducing bank conflicts and channel conflicts. Right? We've seen this. And one key question is how to actually select and randomize bank and channel indices in the address. So what bits do you select to address a bank? What bits do you select to address a channel? We'll take a look at this. Ideally, you would like to minimize the conflicts for concurrent accesses. So this shows you how multiple banks or channels can help. We've already seen this. So advantages of multiple channels, we've covered this. But basically, you increase the bandwidth, you can get multiple concurrent access at the same time. So if you have multiple concurrent access outstanding from your cache, for example, you can get two cache lines if they happen to map to the same channel at the same site service. Disadvantages, you get a higher cost than a single channel because you have more board wires and more pins if your memory controller is actually on chip, on the processor chip. Right? So multiple channels become even more important with multi-core processors because many different processors can request data and they can interfere, they can conflict with each other in the same channel or same bank. As you increase the number of channels, as you increase the number of banks, you get more concurrency. That's why as manufacturers put more cores on chip, they also try to put more channels. Of course, the downside is it's not as easy as putting more cores, right? Putting more cores, you're not increasing the number of pins that you need on the chip. Whereas if you want to put more channels, now you need to add more pins. Which, this is what makes scaling a system to many cores, or a chip to many number of cores, difficult, because as you put more cores, there will be more demand. They'll miss in their caches. There will be more demand for main memory bandwidth. But you cannot increase the number of channels at the same rate as you can increase the number of cores. So you have a problem, right? You have this bottleneck, if you will, between the CPU chip and DRAM system, if you will. And the bottleneck is this. These require pins of the CPU chip, and as you add more cores, they require more bandwidth, which means that at some point, these pins saturate with the data they transfer, and maybe you cannot, putting more cores may not make more sense. So this is called the memory bandwidth problem. It's the same thing that had been experienced with vector processors, right? But it's perhaps more severe because now you can actually generate many more accesses here. Okay, because the processors are much faster also. Okay, so let's get back to address mapping. So there are two major ways address mapping is done in today's systems. How you interleave different things in different places, different portions of memory. One is row interleaving. This essentially says consecutive rows in memory are in consecutive banks. Which means that consecutive addresses in physical memory are in the same row buffer. Right? Does that make sense? So let's say you have bank 0. We've already covered this at a different granularity, if you will. So hopefully you'll remember. Let's say your row size is 2 kilobytes. This means that the first 2 kilobytes in memory, so if you look at the logical view of memory, you divide into rows. And let's say this is the only thing you have in your DRAM system. This is row 0, this is row 1, this is row 2, first 2 kilobytes, second 2 kilobytes, next 2 kilobytes. Row 0 gets mapped here. Row 1 gets mapped here. Row 2 gets mapped here. Row 3 gets mapped here. And so on. So when you bring in a row, you're actually bringing in everything that's consecutive in memory for 2 kilobytes. So if you're streaming through an array, if you will, those accesses all hit at the row buffer if you do row interleaving. Make sense? And like what bits you use, assuming these parameters here, you can see what bits you actually use to figure out what packet. Basically, you select your bank bits after your column bits in this case. So this essentially favors access patterns that have good row buffer locality. Right? The other major method is cache block interleaving. Basically, instead of interleaving the rows, you interleave the cache blocks at a 64-byte granularity across the different banks, or channels, if you will. Which means that you have cache block 0 here, and you have cache block 1 here, and then you have cache block 2 here, cache block 3 here, cache block 4, cache block 5. Does that make sense? So consecutive 64 bytes go to consecutive banks. Now what does this buy you? Let's say, basically, if you're accessing consecutive 64 bytes at the same time, consecutive cache blocks at the same time, you can do those accesses in parallel. Right? And this is especially important when these are mapped to different channels. Now you can perfectly parallelize accesses to consecutive cache blocks. And this could happen when you're actually accessing 2 things at a time. Okay. So there's a big design space related to this. Like maybe this is not the best approach also. And it's a complex design space, so I'll let you think about what happens with different stripes, for example. So it's the same thing as we have seen in vector processors. You can get bank conflicts depending on your mapping and access pattern. Yes?
What is the byte and bus?
Oh, byte and bus is essentially, if your bus is 64 bits, these bits you do not use to address the banks. It's just like a bytes and cache block, right? Those bits you do not use to index into your cache. Okay, so bank conflicts are important. So what can be done is to randomize the address mapping so that bank conflicts are less likely. And this is what some controllers actually do. What they do is, instead of taking bits to determine the bank from one location, they could XOR multiple bits to generate the bank index. Or you could actually have a randomizing hash function if you think to. So this is a randomizing hash function, one example. Very simple. Okay? So with multiple channels, you have more choices. Let's say you have 2 channels. Where do you put the channel bit? Right. We briefly covered this. So I'll let you figure out where are the consecutive cache blocks in this system versus this system. Should be fun. Okay. You remember virtual memory from 213, but there is an interaction with virtual to physical mapping also, right? Remember, virtual address gets translated to a physical address through the TLB and the page table. And that translation affects where an address is mapped in the DRAM system. Right? So if you look at this, this is the virtual address. Let's say that you have a 4 kilobyte page. Your page offset is 12 bits. And this is your virtual page number because you have a 64-bit address space, virtual address space. This is your physical address. You get a physical frame number. An operating system can affect virtual page number to physical frame number mapping. Right? That's what the operating system controls. Now, if you look at the physical address in a different point of view, which is the point of view of the memory controller, basically the memory controller takes these 11 bits as the column address and takes these 3 bits as the bank address. And look, these 3 bits are affected by the translation process, right? And these 14 bits are also affected by the translation process. Which means that if the operating system knows, the operating system implicitly controls what location in the DRAM topology, if you will, which bank in DRAM a physical page goes to, right? Or a virtual page is mapped to. So operating system can do many different things. In modern operating systems, this is not exposed to the operating system. The topology is not exposed, so not a lot of optimizations is done. Okay, but this is something that you guys should think about, because we will get back to this when we talk about virtual memory. Actually, just to let you think a little bit, this is nothing unique to just DRAM, right? This happens in caches also. You get bank bits in caches to figure out, or which index a page gets mapped in a cache, again, is affected by this translation, assuming your index bits actually come from the part of the translation, part of the physical address that changes, that's potentially affected by that translation. So operating system can affect where in the cache, a cache block or a page can get mapped to. And we'll get back to that. Okay, refresh. Some of you are interested in refresh. And this is an important issue. The problem is DRAM capacitor charge leaks over time, right? Which means that if you want the data to be intact in DRAM, you need to have a controller that periodically reads each row and pre-charges it to restore the charge. And this is basically no different than a read operation, except you don't do the read. What the controller does is periodically, every n millisecond, goes through every row address and says, DRAM, activate this row for me, and then pre-charge this row for me. And you have to do this for every row. And typical n in current DRAM specifications is 64 milliseconds. So every 64 milliseconds, this needs to happen for every row. Otherwise, you risk losing data. pretty burdensome, huh? In a sense, you're doing all of these operations just to maintain what you've stored there. And that's the downside of the DRAM technology. Implications on performance, well, when you're activating and pre-charging a row for the purposes of refresh, you cannot use that bank. Right? What if there's an access coming from the processor to that bank? Too bad. I have to maintain the correctness of data. I cannot service you. Right? And this could cause long pause times also. So if you actually refresh all rows in a bank in bursts, every 64 milliseconds, the DRAM bank will be unavailable until the refresh ends. Now, I told you that you can have 16,000 rows in a bank, right? So think about 16,000 rows times the time it takes to activate plus pre-charge each row. 16,000 times 30 nanoseconds. I guess some of you can make the calculations. So if you do this in a not very smart way, you could run into trouble. You could run into responsiveness issues because your request from the CPU is waiting until that entire bank is refreshed. So people have found out better ways of doing this, of course. Instead of doing burst refresh, if you will, all rows, instead of refreshing all rows immediately one after another, you use this distributed refresh. Each row is refreshed at a different time, but at regular intervals. And this figure is from a Micron DDR2 sheet, I think, on refresh. And this figure clearly explains what is burst refresh and distributed refresh. Right? Each pulse, if you will, represent a refresh cycle. And there's some required time to complete the refresh of all rows, if you will, every 64 milliseconds. You could do the refreshes one after another, or you could distribute the refreshes of different rows over that required time. And doing this improves your responsiveness in the memory system a lot better. Yes?
Why not have a separate row decoder to do the refreshes?
Cost. If you have a separate row decoder now, essentially it's a separate port to your DRAM, right?
Right.
It's expensive.
But you don't have to have external pins and stuff, so...
That's true. You could do it internally, but still it's expensive. Right? Still, you don't need to have the external pins, but internally into the DRAM chip it's very expensive. Because you have now multiple ports to each memory row.
Right, but you could also share it across different banks.
I don't know if you could do that. I mean, you could definitely optimize, but
right.
anything you do optimize increases the cost, and that's why it's not done. In fact, what I said here, in existing DRAMs, the DRAM chip itself has some intelligence such that it can do the refreshes also. So what I described to you, activate and pre-charge, you could implement this in the memory controller, or the DRAM chip itself can do it. But when the DRAM chip is doing this, still you cannot access the chip. Because it doesn't have what you said. It doesn't have multiple different ports to the rows. Okay, so back to distributed refresh, this eliminates long pause times. But this is still a problem because refreshes consume power as well as add latency, right? So it's good to think about how else we can reduce the effect of refresh on performance. So I'll tell you some approaches one of my students developed. This is an important problem going into the future of DRAM because what we want is really more memory, right? We want to increase the size of memory. The problem is as you increase the size of memory, this becomes a bigger problem, right? Because you need to refresh every single row. So you really need techniques to eliminate these, if you will. You don't want to refresh something if you really don't need to refresh it. So this is just to give you some numbers on the problem, if you will. These are the capacity of DRAM chips that you currently have, 2 gigabit, 4 gigabit, 8 gigabit. And we break down the refresh power, power consumed by the chip itself, the refresh power and non-refresh power. Today, with an 8 gigabit chip, refresh power is still sizable, if you will. As you increase the capacity of the DRAM chip to 64 gigabits, refresh power becomes significant. I don't know, this is 30% of the entire power. So you're wasting 30% of your power on doing refreshes to maintain data. Yes?
Why does the refresh power, the amount, not change between 4 and 8 gigabytes?
So I think it does change, but I don't know why it's not. Maybe there's a typo here. But that's a good question for Jamie. So I'll ask him. Do you guys know? Okay. It should change unless they employ some technique here that takes advantage of something. Maybe the row size increases when you're going from 4 gigabit to 8 gigabit such that your number of rows is constant. So that could be a possibility actually. And this is the performance impact of refresh, unavailability of devices due to refresh. So again, today, 10% of the time is spent for refreshes. So this is the performance overhead, if you will. But as you increase the size of the chip, 40% of the time, you're going to wait for refreshes. So this is not good. So we need techniques to fix this problem. And one technique Jamie has developed is, what he's observed is, and people have observed this in other ways as well, but DRAM cells have different data retention times. And this is part of the distribution of the retention time. This is the x-axis, the retention time of the cells, and this is the cumulative probability that the cell has that particular retention time. So if you look at a retention time of 128 milliseconds, in a DRAM chip, only 26 cells need to be refreshed every, they have less than 128 millisecond retention time. And about 1,000 cells have less than 256 millisecond retention time. So what this tells you is, not all rows really need to be refreshed at the same frequency. Because there are some cells that keep data for maybe minutes, if you extend this distribution. But there are some cells that keep data for less than 64 milliseconds. But the good thing is, those cells that keep data for very few milliseconds are very few. So you don't have that many rows that need to be refreshed very frequently. The problem is existing DRAM chips are specified to be refreshed at that worst case, every 64 milliseconds. Yes?
Why is it that some cells things are older than other cells?
Okay, that's a good question. That comes from the variability of the DRAM manufacturing process. So it turns out some capacitors are stronger and some capacitors are weaker, and you cannot control that perfectly. Or controlling it makes it extremely expensive to actually manufacture these chips. So you have this distribution of weak and strong capacitors that lead charge at different retention times. Now we can exploit it though, perhaps, if we can somehow expose this to the system. So how can you take advantage of this? Basically the observation is that only very few cells need to be refreshed very frequently. If you can identify the retention time of different rows, we can refresh each row at the frequency it really needs to be refreshed. Right. Let's assume that we can identify the retention time. That's also another interesting problem. But how do you do this? How do you actually implement this? Well, one costly way of implementing this is to store the retention time of each row. Right. But that becomes bad because if you have a 64 gigabit chip, how many rows are there? There are many rows. For each row, you need to store the retention time. And that storage needs to be somewhere. It cannot be in DRAM because that tells you what to refresh. It has to be somewhere. And it can be in SRAM, one chip, but that's very costly. Now the power you use for that would be perhaps higher than the power you use for refresh. So you need a smart way of storing these retention times. And the idea Jamie had was to bin the rows according to their minimum retention times. So don't actually store the retention time of every single row, but bin the rows. And refresh the rows at each bin at the frequency specified for the bin. So for example, you have a bin for rows that need to be refreshed every 64 milliseconds. And that bin contains the rows that need to be refreshed between 64 to, that have retention times between 64 to 128 milliseconds. You have another bin for rows that have retention times between 128 to 256 milliseconds. Now the good thing is, only very few rows need to be refreshed very frequently, every 256 milliseconds, so you can have only a few bins. Right? You can say bin 0, bin 1, and the rest I'm going to refresh every 256 milliseconds. Now the good thing is, this way you have few bins, you store only those bins, so you have low hardware overheads, but you cut down the refresh frequency for most rows by 4x. Instead of refreshing every 64 milliseconds, for most of the rows you're going to refresh every 256 milliseconds. And then you can add another bin, if you will. That ensures that most of the rows are going to be refreshed at 1024 milliseconds, if you will. You have more hardware overhead, but now you cut down the refreshes by 1024 divided by 64. Is that 16? I guess it's 16, yes. 16x.
Do you create these bins dynamically each time you run?
So that's an excellent question, and those are some research questions that Jamie is looking into. You could create them dynamically when the machine boots up. Of course, then you need a very efficient way of creating those bins, right? But actually, the properties do not change across many different ones. So the DRAM manufacturer can store these things in the DIMM, and somehow there needs to be a protocol such that the memory controller gets these bits. Okay. I think Microsoft PowerPoint encountered a problem. That's interesting. Huh? So let's see. Maybe the controller forgot to refresh something. What do you think? Is that possible? More likely there's a concurrency bug in Microsoft PowerPoint. Radiation from space? Oh, I don't know what this is. Is this what we start out with? Okay. So I would like to be able to say this is what happens when you design a memory controller incorrectly, but I don't have enough evidence to back up that claim. But actually, there have been studies done, I think, at different companies, and they found some of the system crashes are actually due to memory errors, because we get bit flips in memory. And I think the number, like if you categorize of all of those crashes, if you will, let's say blue screens, I think about 5% of those are actually due to hardware errors. And usually, most of those hardware errors are due to memory. You get bit flips, or you get something at the memory that is not necessarily identifiable that leads to data corruption, and that leads to a blue screen, if you will. So, I guess circumstantial evidence states that this was more likely a software bug. Okay, so that's the idea, basically. So how do you design a controller that does this? Basically, memory controller, once in a while, generates a refresh candidate, and that's the distributed refresh part of the mechanism. A row address is generated, and this row address is checked in the bin. Is this row in the bin that needs to be refreshed frequently at this time? If yes, then the row is refreshed. Otherwise, you figure out whether the row is in the other bin, and if that bin needs to be refreshed at this point. If yes, then the row is refreshed again. So that's how the controller operates. I will not go into this detail, but maybe we can actually put up the paper so that people can read if they're interested. Yes?
What exactly do you mean by bin? Is the storage thing which you store on the...
Yes. So it's actually you can think of it as a storage. You give it the row address, and then it tells you present or absent, which could be a content associated memory, right? But that's expensive. So what Jamie came up with is to actually implement this with a Bloom filter. You guys know about Bloom filters? No? Well, the idea is very simple. It's a bit vector. There may be more complex Bloom filters, but I'll give you the very simple one. You take the address, and a Bloom filter is used to test whether an address is actually present in the bit vector. Basically, a Bloom filter is a structure, bit vector, that tells you, is the address present? Let's assume that you profile the retention times and figured out came up with a Bloom filter like this, right? You index the Bloom filter with some bits and check whether the bit corresponding to that address is actually set or not set. If it is set, that means the address is present. If it is not set, the address is absent. Right? Does that make sense? So you could think of this bit vector for the entire address space. Right? You could have a bit for every possible address, but that's expensive. So Bloom filter is a compact representation that could sometimes tell you an address is present when it's really not supposed to be present. Okay. So there's aliasing in the Bloom filter. Does this make sense, people? Okay. So basically, it's an approximate structure, if you will, that can have false positive hits. Meaning, it can tell you an address is present when it's not supposed to be because multiple addresses map to the same location. So this Bloom filter can tell you this row actually has retention time that's between 64 to 128 milliseconds, whereas it doesn't. Because it just so happened that some other row that had the same bits mapped to the same address and had the retention time that was 64 to 128 milliseconds, and you had to set the bits because you want to refresh that row, really. So that's the concept of aliasing in the Bloom filter. That's why you get these false positives. Yes, you have a question?
So it's the idea that if there's some address that has that pattern of bits, then you must set the bit, otherwise it is correct.
That's right. Yeah, if there's some address that happens to map to a bit in the bit vector, and that needs to be refreshed within this interval, you set the bit. And if another address happens to map to that same bit, it'll use that bit to determine whether it needs to be refreshed or not. So what this gives you is, now you can have a very small bit vector, right? 1K entries, for example. Which is very fast to access, and you don't have that much storage cost. You'll get false positives, which means that you're going to refresh some rows, even though you don't really need to refresh them at that interval. But you will not get false negatives, meaning the Bloom filter will not tell you not to refresh the row if it needs to be refreshed, because you conservatively set the bits. And that's the important part. As long as your false positive rate is not very high, then this accomplishes the purpose. Right? Okay?
So
Yes?
basically you profile this entire DRAM once and set your Bloom.
That's right, exactly. And that Bloom filter can be stored in the DIMM, for example. Okay, yes.
How do you ensure that, suppose, since it's a manufacturing thing, due to which you have different refresh time, how do you ensure that, suppose there's a chip in which all of the DRAM cells have to be refreshed within the minimum time. So at that time, your 64 to 128 milliseconds DIMM should contain all the rows.
That's right, exactly.
So how do you decide the size of the bin? Is it conservatively decided that if you have such a bad manufactured chip, then it can?
Yeah, so that's a design choice. You're absolutely right. It turns out most of the DRAMs follow this distribution, so your size doesn't need to be that large. Okay, so those are good questions. Okay, so Bloom filter. Going back to Bloom filter. Bloom filter is a structure that's independent of this, right? Bloom filter is just the way this is implemented. I just want to make sure that you guys are comfortable with this. Basically, this is a compact way of presenting whether an address or something is present or absent. Compact way of testing that. So you could use this for many different purposes.
Doesn't the Bloom filter sort of solve the problem he was just talking about? Because if you have some memory that is needs to be refreshed very often, you'll just have many more ones.
Exactly, that's right. That's right. Yeah. So Bloom filter solves that problem also, actually. Basically, let's say all of the rows need to be refreshed at that interval. All of the bits here will be set, and you'll have correct operation,
So a Bloom field vector should have all the rows. Should have one bit for each row.
No. So you could. That's expensive, right?
Yes,
Because
exactly.
so your Bloom filter vector, let's say it has 1K entries, and you use some bits to index. But as you have more rows to be refreshed, the number of the number of bits that is set here increases. So you'll still get correct operation, but you may not be able to save on refreshes. Yes?
So do you dynamically or statically determine like which bits in the address correspond to it?
In this particular case, or in general with a Bloom filter?
Well, like in this case.
Yeah. So that's a good question. That's somebody else asked us before. Also, you could determine this at the manufacturing time of the DRAM, or you could profile it when you boot up your system, for example. Maybe you should read the paper. We'll post the paper if you're interested in this, because there are other issues. Like actually, refresh time turns out to be dependent on temperature. As temperature increases, you need to refresh more frequently. So you need to adapt the system, and the paper describes how you adapt the system to refresh more frequently. Okay. So let's move on from the refresh. Looks like you guys are interested. But that's a bigger problem going into the future with DRAM, and that's one of the reasons why industry as well as researchers are exploring technologies that are non-volatile. So if you have non-volatile memory, you don't have this refresh problem, right? DRAM is volatile memory. It loses the data. Well, it loses the data in two ways, right? One is while it's powered on, it loses the data. So it's doubly not volatile, if you will. And it also loses the data when it's not powered. It doesn't matter. And powered means you're actually connected to a power source. Whereas non-volatile memory, like a hard disk, it doesn't lose data regardless of whether or not it's powered. Right? So if you can build a main memory with non-volatile memory, like phase change memory, for example, or flash memory, then you don't have this problem. Right? So that's one way of eliminating refreshes. The downside is there are downsides to these other technologies as well. They have much longer latencies to access. Okay, so DRAM controller. So hopefully you have a glimpse of what the DRAM controller does by now. First and foremost, it needs to ensure correct operation of DRAM, right? Both in terms of refresh and in terms of obeying these timing constraints. So DRAM controller should not send multiple commands to DRAM at the same time, because some of the behavior of DRAM is unspecified if you actually do multiple activates at the same time. It's not clear what happens. So there is a protocol, DRAM protocol, that's obeyed by the controller and the manufacturer to ensure correct operation. And the DRAM controller needs to obey that. It needs to service DRAM requests while obeying the timing constraints. So constraints are essentially resource conflicts and minimum delays. This is one example, write-to-read delays. But there's also a minimum delay between multiple activates. There's also a minimum delay between multiple reads. It needs to buffer and schedule requests to improve performance. It needs to do reordering if you want to improve performance, right? It needs to manage the row buffers, keep track of which bank has which row active. And it also has other duties today, especially. It needs to manage power consumption and thermals in DRAM. So many memory controllers turn on and off DRAM chips or manage power modes to minimize the power in DRAM. You can think of this as many cores, many controllers for processors changing the power modes of the processor, changing the voltage and frequency. Are you guys aware of that? It's called voltage and frequency scaling, dynamic voltage and frequency scaling. So DVFS, or dynamic voltage and frequency scaling. I'll give you the buzzword. And the idea is, if a processor doesn't need to run at the maximum frequency, why don't we reduce the frequency dynamically, such that the clock doesn't need to go up and down as fast? Right? Now, what does this do? This saves power. You could do a similar thing at the memory controller also. But maybe we can go into that when we talk, if we get a chance to talk about power. But similar, the idea is when a resource is idle, if a resource is idle, save power by either turning off the clock to it, or reducing the frequency by reducing the frequency of the clock. That way you don't essentially switch, that logic doesn't switch. And do you guys know why power is consumed? Have you covered it in previous classes? So there is a fundamental equation. I'm not going into the detail, but power essentially correlates with this. It's the capacitance of the circuit, voltage, times frequency. Right? Does that make sense? Have you guys seen this before? Some of you have. Okay. Voltage squared and frequency. And there is also some factor. This is how active. Let me call this the dynamic power, actually. This is the switching activity, if you will, in the circuit. And it depends on whether you switch the data, whether you switch the transistors. So obviously, if you want to minimize power, you would like to minimize all of these. And frequency, if you reduce the frequency, your power goes down. If you reduce the voltage, your power goes down quadratically. Now it turns out in existing designs, you need higher voltage to support higher frequency. So when you don't need higher frequency, you can also scale down the voltage. It takes more time, but you can do that in existing designs. So if you do that, if you're not using a part of the core, for example, let's say your core is waiting for a memory request, very long latency memory request, an I/O request. That's going to take, 1,000, 2,000 cycles. Why don't you scale down the frequency of the core? And at the same time, why don't you scale down the voltage of the core? Now your power goes down in a cubic manner, right? And that's the idea of dynamic voltage and frequency scaling, to reduce the power when you don't need the performance from the core. Does that make sense? That's one principle of saving power. I guess we're talking about power, so I'll give you the other principle that's employed in existing systems. Principle one, reduce the frequency and the voltage. Principle two, turn off circuitry that you don't need. That you do not need to use. For example, if you know that you're not going to use the floating point divider, turn it off. Turn it off, what does that mean? Basically, there are ways to gate the clock and gate the power. These are actually power lines, the VDD or VCC, depending on what course you've taken. You can actually gate these lines such that the circuit doesn't leak. It doesn't consume static power. So this was a dynamic power equation. You can gate the clock to reduce the dynamic power. And what does gating the clock mean? Basically, you have this clock signal, right? And that's connected to an AND gate, if you will. And this clock gate controls the clock that's going into your latch, for example. Let's say you have a latch. And if this clock gate is turned on, well, I guess you could have a clock gate bar or something like that, right? If this clock gate is turned on, you get 0 always out of this, which means that you're not clocked anymore. Which means that your circuit doesn't switch, which means that your activity gets reduced, right? The switching activity goes to 0. So you don't consume dynamic power in that piece of the circuit. So you could think of dividing a chip like a floating point units. If you're not using the floating point units, you have the clock signal here, and you have the AND gates, and you have the clock gate signal controlled by some logic. If you're not using the floating point unit, you set the clock gate signal. I guess let's do this bar. Okay? That way you don't consume dynamic power. I'll get to you soon. How do you say static power? So static power is consumed when the circuit leaks, right? Even if you're not using the circuit, there's some leakage that happens through the transistor, right? Remember, I guess an inverter, you have basically, even if the circuit is not turned on, the charge leaks from, again, VDD to ground. There's some leakage or static current, if you will. And you can represent any circuit in kind of like this form. There's always a path from the VDD to ground that charge leaks. So how do you actually save this? And that's the idea of gating the power. You could have transistors, and there are different ways of doing this, that gate this VDD such that the VDD is not supplied to the circuit. And this is sometimes called a sleep transistor, if you will. In a sense, you put the circuit to sleep. If you enable that signal, the power is not supplied to the circuit, and now you cut down that leakage. So how do you do that? Well, if you know that you're not going to use this FPU, floating point unit, you have a signal that says also power gate. Now you can eliminate the static power as well as the dynamic power from the circuit. And this, that way, essentially, you're cutting off any power that's consumed by the circuit. And these are powerful techniques. These are powerful principles. Make sense? I've taken the liberty of moving to power a little bit, but that's a very important concept, especially in today's designs. We talk a lot about performance in the course, but this is equally important. Because if you do not do this, then you're limiting your performance as well. Right? Why? Because now you're consuming power unnecessarily, which means that you cannot put another core on the chip, perhaps. You cannot put more cache on your chip because you're not managing your power intelligently. And remember, there's limited power. There's a total design power, or thermal design point also. I like calling it total design power as well. That determines the maximum power you can supply to the circuit. And if you're wasteful in how you actually use that power, your performance gets affected significantly. Because you cannot do more with what you have, with the resources you have. Make sense? So power consists of dynamic power plus static power. Dynamic power is this. Static power is dependent on how much leakage you have. And you can reduce power in different ways. Basically, turn off the clock if you're not using the resource, and turn off the power if you're not using the resource. And you can say both. Yes, you had a question. Or did I answer it?
No, basically, I thought gating clocks can sometimes be bad as well, right? Because if you have some noise on your clock gate signal, then it could mess up like normal operation.
That's right. I mean, that's right. You have to make this work. In a sense, you have to make sure that this doesn't interfere with your normal operation. I mean, there are other concerns, of course, right? Let's say you turn it off. There's always a latency to turn it on, turn it back on. So you need to carefully consider the decision of whether you turn up, when you turn off, and when you turn on. Because let's say you turned off your floating point circuit, and one cycle later you get a floating point instruction. Well, you need to turn it back on now. But turning it back on, especially if you do power gating, takes time. It takes some number of cycles. So let's get back to the DRAM case. Some DRAM chip, you're not using it for some reason. The data is not mapped to it. Right? You can turn it off to save both dynamic and static power. The downside, when you need it, when you need to allocate data to that particular chip, now you need to turn it back on. And that takes time. Okay? Okay. We have a bunch of issues in memory. DRAM controller. One important issue is where to place the DRAM controller. Do you put it on chip, where the CPU is, or do you put it off chip? Does it have a separate chip, if you will? Is there a separate DRAM controller chip? And this is how things used to be until very recently. There was a separate DRAM controller chip that controlled memory. But as we are able to put more transistors on chip, DRAM controller was one of the first things that went onto the processor chip. But there are advantages and disadvantages to each, actually. It's not a clear-cut design choice. If you actually have a DRAM controller chip that's separate from the processor chip, now you have a lot of flexibility, right? You can have a separate controller chip for different DRAM types, and there are many of them, which we haven't covered. But, for example, graphics has a different DRAM type. Graphics DDR, it's called. Or there are different protocols as well. You have more flexibility to plug different DRAM types into the system. And you have less power density in the CPU chip, right? We just talked about power, and this is the appropriate thing. Which means that you have one less thing in your chip to worry about. But on CPU chip, if you actually put the controller on the chip, now you have reduced latency for main memory access. Why? Because you don't need to go off chip to a controller chip and then off chip again to another, to DRAM. I don't remember where I put this. But it's like more hiding here. So this is your CPU chip, and this is your memory controller chip, and these are your DIMMs, if you will. If you put the memory controller off chip, then the latency is high, because these wires are much slower than the wires you can put and clock on your core. This is option 1, I guess, on chipset. This is option 2, we can do here. CPU, and you have memory controller on the CPU. This is the second option, and it connects directly to the DIMMs. Memory controller is integrated on the same chip as the CPU. That way, you get reduced latency, and you get higher bandwidth between the cores and the controller, right? Here, you're pin limited. The information that you communicate should be very small. Here, you're not pin limited. This is all on chip. So you get higher bandwidth. And you can think about optimizing the performance in different ways, and we will talk about that. Okay, so what does a DRAM controller look like? This is, let's look at this. So it has many functions. It's connected to the DRAM here, and there's some signaling interface, the I/O pads, for example. But before that, it gets on the other hand. On the other side, it gets requests from the CPUs, also as well as I/O devices. Remember, I/O devices, if you have memory mapped I/O, I/O devices that can actually transfer data into main memory, like if you have direct memory access, for example. So they all, there is an arbiter that actually arbitrates between the request streams, requests coming from here. If you have multiple ports, you can assign them right away here into the banks. But you have also request buffer queues, this is one example, that can buffer the request for each bank. Again, you could think of a centralized queue as well for all banks. Again, dynamic versus static partitioning. In this case, I guess I kind of show you queues for each bank. And you have a scheduler here that picks which request should be scheduled next. So if we look at this part in a little bit more detail. The modern controller, let's look at the on-chip controller here. You have requests from different caches that could go to any bank, and each bank has its own request buffer. These store the requests coming from the cores, and each bank can have a scheduler that decides which request to prioritize next. And one option could be the scheduler says, I'm going to find, I know which row is open in this bank, and I'm going to find and prioritize the request that goes to that row. Right? That could be scheduling policy here. If I don't have any requests that go to that row, I'm going to find the oldest request in the request buffer and schedule that. It's a very commonly used scheduling policy, although it has changed over time. And bank 0 picks a request from its request buffer. Each bank picks a request from its request buffer. Of course, if a request cannot be picked, then they will not pick it. And then there's another level of scheduling that picks among the requests that each bank scheduler has picked. Because you have a single command and address bus shared by all banks. You cannot send more requests than the address and command buses you have. Okay? So some scheduling policies. First come, first serve. This is pretty simple, right? Oldest request first. You could employ that in each bank. Also, you could employ that in the bus scheduler. Each bank picks the oldest request in its request buffer, and the bus scheduler also picks the oldest request among all of those requests suggested by each bank. Of course, this is almost no scheduling. I can just pick the oldest one that arrives. In fact, many memory controllers, the chipsets that were designed for Pentium 4, for example, did this until very recently. Simple, first come, first serve. Most controllers are a little bit more intelligent because they want to take advantage of this row buffer hit latency. There's a significant difference. So what they do is they prioritize requests that are row hits, and if all else being equal, they prioritize requests that are older. So if you have 2 row hit requests to the bank, you prioritize the one that's older. The goal is to maximize row buffer hit rates and maximize DRAM throughput, minimize request latency. Just one point, scheduling is actually done at the command level. So you don't actually send a request, and this is clear, hopefully. You have column commands, and you have row commands, and each request requests basically for each request, the controller keeps track of, does this need an activate at this point? Does this need a pre-chart? Does it need a read? Does it need a write? And then among those, it schedules. Okay? So one way of implementing this FRF-CFS is, if you will, prioritizing requests that are waiting for the column commands. Because obviously, if you're waiting for a column command, you're a row buffer hit. And or those that are waiting for the row commands. And within each group, older commands are prioritized over younger ones. Yes?
If you're putting this memory controller on chip, like on your CPU and like having the interface to the DIMM, then aren't you like really coupling it with the protocol of the DIMM because it's done at the command level?
That's right, exactly. Yeah, that's right. Yeah, you are coupling. So this protocol now has to be the protocol specified by the DIMM. Whereas here, it doesn't need to be. So you have more flexibility, if you will, here.
So the DIMM in the first case, in the second case cannot change.
In this case.
Yeah.
So basically, you're limited by, you have limited choices to what you can implement here. Make sense? Yes?
So what if you have received cores and core A keeps making requests to the same memory location over and over again, and then core B wants to make requests to something within the same bank but a different location, and then core A just take all of the
Exactly.
to that.
And we'll see that. Yeah, we'll get to it. So a scheduling policy is essentially a prioritization order. This could be based on many different things. Request age, row buffer hit miss status, and this is what modern controllers look into. Request type, requester type, load versus storm for example, or prefetch, read, write. Request criticality. I mean, there are different ways of designing the scheduling policy. Many controllers don't look into these things, but we propose a lot of mechanisms to actually look into these things, and I'll tell you a couple of those, that some of which are hopefully being implemented soon. But before that, let me look into a couple of other things. Row buffer management. This is actually another thing that determines DRAM performance significantly, right? Remember, open row. So you would like to maximize the locality in DRAM. One policy is to keep the row open after an access. Another policy is actually close the row after you do an access. So how do you do that? You can pre-charge the row after you finish the access. Right? So there are trade-offs associated with this. If you have an open row policy, if the next access is to the same row, then you get a row hit. Right? So open row policy says keep the row open after an access. Don't do a pre-charge right after the access. But the downside of open row policy, if the next access goes to a different row, now you have a row conflict. You could have pre-charged the row right after you accessed it the first time, and when the next access comes to the same bank, it doesn't need to wait for that pre-charge latency. Does that make sense? If the accesses are interleaved such that they're a little bit farther from each other, then you don't need to incur the row conflict latency if you actually have a closed row policy. So closed row policy says close the row after an access. Well, the smart one says if no other requests already in the request buffer need the same row. So a very strict closed row policy says after every access close the row. A smarter one, well, take a look at the request buffer first. If there is some request going to the same row, then don't pre-charge the row right away. Pre-charge the row until all of the requests to that row are out of the request buffer. So that's what's implemented in some processors, actually, some memory controllers. The upside is if the next access goes to a different row, you avoid a row conflict early on. You don't need to incur the pre-charge latency. But if the next access leads to the same row, then you have an extra activate latency. So it's pretty simple, hopefully. So if you want to get the best of both worlds, you should design an adaptive policy. Meaning, predict whether or not the next access is going to go to the same bank, whether or not the next access to the same bank is going to the same row. And if your prediction says it is to the same row, keep the row open, otherwise close the row. And some memory controllers have proposed to do this also. So this is just to give you an example. I'll let you study this. But I guess one example is here. If you have closed row policy, and the first access is to row 0, and the next access is to row 0, and access is not in the request buffer when the row is about to be closed, this is bad because you need to activate the row, read the row, and pre-charge the row. Whereas with an open row policy, you just need to do a read. So there are advantages and disadvantages to each policy. Why are these controllers difficult to design? Well, I told you that you need to obey DRAM timing constraints, and I've given you a couple of them. But if you look at a modern DRAM device, there are many, like more than 50 timing constraints that the controller needs to obey. Like one example, for power reasons, you have a constraint saying four activate windows. You cannot actually do 4 activates at the same time. Do more than 4 activates at the same time. So your controller needs to take these into account. Obey the protocol to ensure that your data stays intact. Other things, for example here, write to read delay. There is a minimum number of cycles to wait before issuing a read command after a write command is issued. So these complicate the design of this controller. It also needs to keep track of many resources to prevent conflicts, and as your DRAM system becomes more complex, your controller becomes more complex. You needs to handle DRAM refresh on top of all of this. And on top of this, if you want good performance, it needs to optimize for performance. It needs to reorder requests. And that's not simple, right? It's not as simple as first come, first serve. So what logic do you need to reorder requests and determine which request hits in the row buffer. You have a request queue. Each queue entry has the row address it's accessing. And you have the address of the row that's currently open. What do you need to do? Exactly, yes. A prioritized content addressable memory. Right? You take the row buffer, the address of the row in the row buffer, and you need to compare it to each location to figure out whether the request fits in that row. And you need to also have a priority based on the age. Right? So it's not as simple. And we haven't even talked about more complex policies. Okay. So, and doing this, especially in the presence of all of the other constraints, make these more complicated. Okay, so this is just to give you an example of a bunch of just, I guess 1, 2, 3, 4, 5, 6, 7, 14 of the DRAM timing constraints. As I said, there are more than 50. Okay, power management, we briefly talked about this. There are power modes in these chips, and the idea is when not accessing a chip, power it down. And there are a bunch of power states. What makes it complicated is state transitions incur latency, during which the chip cannot be accessed. So the lowest power mode is self-refresh mode. We've talked about refresh. You can put the DRAM chip into a mode such that the data integrity is maintained. The chip itself does refreshes, but you cannot do anything else with the chip. So for example, when your cell phone is not being used, very likely it's in self-refresh mode. The chip itself does the refreshes. The controller doesn't need to deal with it. The chip has automatic circuitry to do this. And that's the lowest power mode. But you still need to do refreshes. Now, when your cell phone is turned off, and if you actually need to access something in memory, and if the chip is in self-refresh mode, there's some latency it takes to get the chip out of that mode to enable the next access. And that's the longest latency. Because this is the lowest power mode, it takes longer to get out of it. Because there's setup time associated with what the chip is doing. Okay. Maybe this is a good place to stop. Actually, it is a good place to stop. We'll pick this up in the next lecture.